forced convection empirical correlations. Okay, so if you're a first-year chemical engineering student, you've definitely seen this table. It's basically your go-to guide for calculating heat transfer rates, that all-important H value. It all comes down to using key non-dimensional numbers, like the Nusselt, Reynolds, and Prandtl numbers, to figure out how the fluid is really behaving. First up, let's talk about flow inside a tube. You can't just use one equation for everything, right? If your flow is fast and turbulent, you're going to use a robust formula, like the Dittus-Boelter equations. But if it's slow and smooth, what we call laminar flow, that's a whole different story, and it needs its own set of formulas. Even the entrance of the pipe has its own special correction. Second, things change completely when you have flow moving around an object instead of inside it. Think about fluid flowing across a cylinder or a sphere. The way the fluid's boundary layer forms is totally different. It creates this wake behind the object, which is why we have totally separate equations just for these external flow situations. And finally, what about pipes that aren't circular? Well, this is where engineers use a really clever tool called the hydraulic diameter. We basically calculate an equivalent diameter for something like a rectangular duct. This is a real game changer, because it lets us use all those standard, well-tested tube flow equations for almost any shape you can imagine. So these correlations are powerful tools for real-world design. But you've got to be careful. The key is always matching your specific problem, the flow range, the geometry, to the right equation's restrictions. Let's dive into more detail.
All right, let's talk about one of the absolute cornerstones of chemical engineering, forced convection. Now, forget everything you think you know about just memorizing formulas from a textbook. We're going to look at this in a whole new way. By the end of this, you'll see it for what it truly is, a powerful, practical toolkit that you can use to solve real-world problems. I mean, just think about it for a second. You've got all these different problems, right? From tiny microelectronics to these massive industrial processes. They all share one big challenge. How do you move heat from point A to point B efficiently using a moving fluid? They're all forced convection problems. So the real question is, how do you go from that problem on a piece of paper to an actual working design? Well, here's the good news. You don't have to start from scratch. Not at all. You get to stand on the shoulders of giants and use the collected wisdom from countless experiments, all boiled down into a, pretty dense table of equations. Now, I know that sounds scary, but we're going to change how you see it. This isn't a list to memorize. It's a toolkit. And today, you're going to learn exactly how to use it.
So here's our game plan. First, we're going to open up this toolkit together. Then we'll get you fluent in the language of these tools. After that, we'll figure out how to pick the right one for any job, walk through a classic example, and finally, I'll give you a super simple 5-step method to tackle any problem you come across. Let's get started.
Okay, here it is. This might look familiar. Table 6-8 from your textbook. It's the source of so much engineering power. And maybe, just maybe, a little bit of anxiety. But don't worry, we're about to demystify it. I get it. At first glance, this is just a wall of symbols and equations. But if you look a little closer, you'll see it's actually really organized. See, you've got sections for different scenarios, flow in a tube, flow across a cylinder, flow over a sphere. Every single equation here is a specialized tool designed and tested for a very specific job. Your goal isn't to memorize them. It's to become that skilled mechanic who knows exactly which wrench to grab. All right, before we can use these tools, we've got to speak their language. And in the world of fluid dynamics and heat transfer, that language is built on something called dimensionless numbers. Let's break down the 3 big ones you absolutely have to know. First up, the Reynolds number, or RE. I love this one. Think of it as the flow's personality test. A low Reynolds number means the flow is laminar. It's smooth, it's predictable, kind of like honey slowly pouring out of a jar. But a high Reynolds number, that means the flow is turbulent. It's chaotic, it's swirling like a raging river. And that difference between laminar and turbulent is probably the single most important decision you'll make when you start a problem. Next, we have the Prandtl number, PR. So if the Reynolds number told us about the flow's personality, the Prandtl number tells us about the fluid's thermal personality. It's a property of the material itself. What it does is it compares how fast momentum spreads through the fluid versus how fast heat spreads. For example, liquid metals have really low Prandtl numbers. Heat just zips right through them. Oils, on the other hand, have super high Prandtl numbers. This number is key to understanding what's going on right at the boundary. And finally, the Nusselt number, nu. This is the prize. This is what we're solving for. It basically tells you how much better your heat transfer is with the fluid moving, that's convection, compared to if the fluid was just sitting still, that's conduction. So a high Nusselt number means you're doing an amazing job moving that heat around. So let's just put that all together. We use the Reynolds number to figure out the flow. We use the Prandtl number to understand the fluid's properties. And then we use both of those numbers to solve for the Nusselt number, which tells us how good we are at transferring heat. Pretty much every single equation in that big toolkit of ours is just a relationship between these three.
Okay, so you've got this big table, this box full of tools. How in the world do you pick the right one? Well, the great news is it's not guesswork at all. It's a clear, logical process of elimination.
You just have to ask yourself 3 simple questions. First, what's the geometry? Are we flowing inside a pipe, or is it flowing across a cylinder? That question alone will knock out most of the options in tables 6 to 8. Second, what's the flow regime? You calculate the Reynolds number. Is it laminar or turbulent? Boom, now your options are even smaller. And third, and this is important, check the restrictions. Every equation has fine print that says, hey, only use me when Reynolds is in this range and Prandtl is in that range. If you match all 3, you've found your tool. Simple as that.
All right, let's make this real. Let's put this process into action. Flow inside a cube is probably the single most common forced convection problem you're ever going to see. So for our case study, let's say our geometry is a tube, and we've already done the math and found a high Reynolds number, so we know for sure the flow is turbulent. So we open up our toolkit and we find a couple of options for turbulent tube flow. Here are 2 of the big ones. On the left, you've got the Dittus-Boelter equation. It's a fantastic all-purpose tool. On the right, we have the Cedar-Tate equation. Now look closely. It looks almost the same, right? But it has that one extra term at the end. That little piece is a correction for how the viscosity changes when there's a big temperature difference. So you'd grab this more precise tool if you're, say, cooling a very thick viscous oil, where the fluid at the hot wall behaves way differently than the fluid in the middle. It's a perfect example of picking a more specialized tool when the job demands it. And honestly, the toolkit just for flow in tubes is huge. There are different equations for laminar flow, different ones for when the tube is rough instead of perfectly smooth, special tools for the entrance of the pipe where the flow is still developing. There are even ways to handle things that aren't circular pipes, like a square duct. For every specific condition, there's a specific tool just waiting for you. Okay, you know the language, you know how to pick your tool. Now let's put it all together into a repeatable workflow, a method that's going to get you from the problem statement to the final answer every single time.
Here it is, your 5-step method. Step 1, find all your fluid properties, density, viscosity, all that good stuff, at the right temperature. Step 2, calculate the Reynolds number. This tells you if it's laminar or turbulent. Step 3, calculate the Prandtl number. Step 4, now using the geometry, the Reynolds number, and the Prandtl number, you go to your toolkit and select the perfect equation. And finally, step 5, you solve that equation for the Nusselt number. From there, it's easy to get the heat transfer coefficient, H, and once you have H, you can find the total heat transfer rate. That's it. That's the whole workflow.
Now, before we finish, we have to talk about the real world for just a second. This quote from the source material is so important. All of these neat, beautiful equations were developed under perfect laboratory conditions. But out in a real chemical plant or inside a real car engine, things are, well, they're a lot messier. And that brings us to the most crucial point of all. These equations, they are not magic. They are incredibly powerful, well-tested tools, but they're still just tools. Your real job as an engineer is to use your judgment. It's about knowing when a simpler equation is good enough, understanding where errors might come from, and making smart, informed decisions based on these numbers. The table gives you the calculation. You provide the engineering wisdom. So there you have it. That intimidating table of equations isn't so scary anymore, is it? It's an open toolkit, ready for you to use. You can speak the language, you know how to pick the right tool for the job, and you have a clear method to get to the answer. The only question left is, what problem are you going to solve first?